Hi, as promised in this video we will discuss the answers to the Snowball exercise. The full answers are of course also available in a PDF on Brightspace. As stated, we had two objectives. One, to explore the effects of where aircraft fly and the implications this has for the various design requirements of the structure and materials used, and two, to investigate the snowball effect, which describes how inducing the weight of one structure induces other weight reductions, which snowballs to further decrease aircraft weight. So let us start with the answers to part 1 on pressurization. A positive pressure difference indicates a higher air pressure in the cabin than outside the aircraft. The question was, explain why this overpressure is necessary. The answer we were looking for is overpressure is the condition where the air pressure in the cabin is higher than the air pressure outside the cabin. P cabin is greater than P external. This overpressure is needed so that passengers and live cargo can breathe normally during the flight and that the temperature of the cabin can be maintained at a comfortable level. Question 1.2 is, an aircraft is flying at an altitude of 11,000 meters. If the cabin is pressurized to an equivalent altitude of 3,000 meters, calculate the pressure difference delta P between the cabin and the outside air. So to get the answer, first you look up from Appendix A in Anderson the atmospheric pressure at 3,000 meters and again at 11,000 meters. Then calculate the difference between the two, which gives 0.048 megapascal as delta P. And the final question of part 1 on pressurization. For passenger comfort, an aircraft manufacturer would like to design a cabin made of composite materials that pressurizes to an even lower equivalent altitude by increasing the cabin pressure. Calculate the pressure difference between the cabin and the outside air if the cabin pressure is kept at sea level. Again, for the answer, look at Appendix A from Anderson to look up the atmospheric pressure at sea level, which is 101,325 pascals. The new pressure difference then becomes 0.078 megapascals. Now let us look at part 2 of the assignment, the fuselage stresses. When designing an aerospace structure, the allowable stress, sigma allowable, should not be exceeded. Why is there a large difference between sigma allowable and the tensile heat stress, sigma y, and the tensile failure stress, sigma max? Well, the answer is that the values for sigma allow used for calculations are typically much smaller than that for sigma y or sigma max. There are a few reasons for this. Firstly, when doing calculations, a number of assumptions and simplifications are made. There are also uncertainties in the real event that only can be predicted by statistics, which have a level of confidence lower than 100%. Secondly, the values given for sigma y and sigma max are for pure tension. When an aircraft is flying, however, other load cases can also occur, and often simultaneously, such as shear forces, fatigue loading, and buckling due to compression. Each of these cases also have specific failure limits. For example, the failure limit for fatigue in an aluminium alloy 2024 T3 is 80 to 100 megapascal. You were also asked to calculate the required thickness for each pressure vessel with the following parameters: radii of 1, 2 and 3 meters, delta P of half a bar. So let's have a look on how you have to do this. We will illustrate the calculations by working two materials out in detail for only one radius. We will use one metal, 2024 T3 aluminium, and a 50% fiber content UD carbon epoxy composite. First, let's look at aluminium 2024 T3. From the table you were given, sigma allowable for aluminium is 85 megapascals. Also given is that delta P is equal to half a bar, which is equal to half a kilopascal or 0.05 megapascal. The hoop stress is given by sigma hoop being equal to delta P times R over T, and this must be equal to sigma allowable. If we rewrite this, we get that T hoop is equal to delta P times R over sigma allowable, and if we substitute the numbers, you get 0.05 times 1 over 85, which gives 0.0059 meters or 0.59 millimeters. Next, the longitudinal stress. The formula for longitudinal stress is delta P times R over 2 times the thickness in longitudinal direction. To calculate the minimum thickness in longitudinal directions, this formula must be equal to sigma allowable. This gives that the thickness for the longitudinal stresses is equal to delta P times R over 2 times sigma allowable. Substitution gives 0.05 megapascal times 1 meter over 2 times 85 megapascal, and if you do the math, this gives a thickness of 0.00029 meters or 0.29 millimeters. We've now found two minimum thicknesses. 0.59 millimeters as minimum requirement in hoop direction and 0.29 millimeters as minimum requirement in longitudinal direction. The bigness thickness is governing, as it's the only one that meets the requirements in both directions. Hence, the minimum thickness is 0.59 millimeters. Now for carbon epoxy unidirectional fiber with a 50% fiber content. Sigma allowable from the table is 250 megapascals. Delta P is again a half a bar or 0.05 megapascal, and the radius is 1 meter. We again equate sigma hoop to sigma allowable, which is equal to delta P times R over T hoop to get the minimum required thickness in hoop direction. T hoop can be expressed as delta P times R over sigma allowable. Substitution gives 0.05 times 1 over 250, which results in a thickness of 0.0002 meters or 0.2 millimeters. Similarly, we can now calculate the minimum required thickness of the composite in longitudinal direction by equating the longitudinal stress to the allowable stress. The minimum required thickness can then be expressed as delta P times R over 2 times sigma allowable. Substitution gives a thickness of 0.0001 meters or 0.1 millimeters. Again, we have two thicknesses, but this time we have an anisotropic material. UD stands for unidirectional, so only carries loads in one direction. So T hoop is the required thickness for the UD layer in hoop direction, and T long is the required thickness for the UD layer with fibers in longitudinal direction. To satisfy sigma allowable in both directions, we must add the two together. T is equal to T hoop plus T long is equal to 0.2 plus 0.1 is equal to 0.3 millimeters. If you do all your calculations, this is what the complete set of results should be after you've completed them. Hopefully, they match. In this question, you were asked to plot the thickness calculated in question 2.2 versus the allowable stress for each radius. What trends can you notice? So let's have a look at isotropic materials. The plot should look something like this. Two relationships can be identified here. One, across the range of materials, as the allowable stress increases, the required skin thickness decreases. And two, for a given material, the required skin thickness increases with increasing radius. You may also be wondering why only isotropic materials are plotted. Remember that because the composite materials are anisotropic, T composite needs to be the sum of T hoop and T longitudinal. For isotropic materials, T hoop is sufficient to withstand both stresses and therefore is the only value that ends up being plotted. If we also plot the T composite values for simplicity, using only R as 3, the trend is no longer visible, as you can see from the two circles. But if we only plot T hoop for the composite materials, they fall in line with the trend. We talked in class about metals yielding before reaching sigma max, while composites do not yield before sigma max. What is the advantage of using material which yields prior to failure? The answer we're looking for is that certain materials, such as metals, first deform plastically before failing, while other materials, such as composites, simply break. This can easily be illustrated by comparing how an Aero or Bros chocolate bar breaks versus a caramel-filled bar. Materials that yield prior to failure retain some residual strength, allowing a bit more time to detect issues prior to final failure. If you recall the difference between delta P in the aircraft in questions 1.2 and 1.3, if the aircraft in question 1.2 is a primarily aluminum structure and the aircraft in question 1.3 is primarily made of composites, what are the design consequences of these pressure differences? It's important that you motivate your answer. In the composite aircraft from question 1.3, the pressure difference is much larger and therefore requires a higher skin thickness. Because the fuselage is made of composite materials, however, the increase in skin thickness does not increase the weight as dramatically as increasing the skin thickness of an aluminum structure. Now let us look at the answers for part 3 on the specific material properties. If you want to compare the relative weight of pressure vessels with the same radius but different materials, what equation should you use to calculate which pressure vessel will be the lightest when comparing materials of the same radii? The weight of a pressure vessel, idealized as a cylinder, is determined by its size and material density. The volume V of a cylinder is given by V is equal to 2 times pi times the radius R times its length L times the wall thickness T. Following from this, the weight W of a cylinder is given by W is equal to the volume V times the density ρ. When comparing cylinders with the same radius R and length L, these terms cancel out. So resulting in W1 over W2 being equal to T1 rho 1 over T2 times rho 2. Therefore, to compare the weight of a set of cylinders with the same radius, the weight equation can be reduced to the relative weight is equal to the thickness T times the density rho. Now for question 3.2. Using the thicknesses calculated in question 2.2 and the equation obtained in question 3.1, calculate the relative weight of each pressure vessel. Similar to question 2.2, example calculations are given for one metal and one composite material, using the thicknesses calculated in part 2. Note that T is in millimeters, so you must divide by 10, which gives 0.16 gram per centimeter squared for 2024 aluminium and 0.54 gram per centimeter squared for 50% fiber content carbon epoxy composite. Next question is to briefly discuss a few criteria that you could use to select the best combination of pressure vessel radius and material. Of the combinations you calculated, which would you consider the best? Let me discuss some of the criteria with you one by one. Weight. The structure has to remain airborne and therefore should be as light as possible. A lightweight structure also means your aircraft will require less fuel to fly the same distance. And if we look at thickness, if a skin material is too small, the material is very fragile and is vulnerable to damage during handling and impact. Additionally, it's much more susceptible to buckling under compression or shear loads. All of this will be covered in much more detail in part 2 of this course, Introduction into Aerospace Engineering, part 2. Other criteria you can think of are cost, sustainability, manufacturing process, material availability, processing time, and customer requirements. And there are probably many more you can name. So when designing aircraft, there are always several criteria to consider. It's up to the engineer to determine the importance of each criterion in the context of the design. In this case, you have the relative weight and thickness of the different cylinders. So if we look at our table here, what choices would we make? In our example, a low relative weight and a mid-range thickness were considered desirable. So therefore carbon steel is excluded based on its relative weight, since it has a much higher relative weight compared to the other materials for all radii. Similarly, high-strength steel is excluded due to its low thickness. None of the other metals have particularly outstanding properties. Looking now at the composite materials, we see that the carbon epoxy material is more desirable in the relative weight category, but glass epoxy has a slightly larger thickness at all radii, making both materials desirable options. At this point, it's up to the engineer to decide which criterion they consider more important and make a selection. You would like to investigate the design of a pressure vessel under a different load case, specifically pure bending. Would you expect your result to be different compared to the pressurization load case? Why or why not? Well, yes, in short, the results would be different. In bending, one side of the structure is in tension, while the other side is in compression. The compression side is susceptible to buckling if the thickness is not sufficient. Therefore, a thicker but still lightweight design is ideal. And now for the final part of the assignment, the snowball effect. Due to the engineering efforts, the aircraft empty weight has been reduced by 2,000 kilograms. Calculate the total weight reduction of this change due to the snowball effect and use at least 5 iterations. In each iteration cycle, you will need to calculate 4 additional parameters: the thrust T, the maximum thrust T max, the engine weight Weng, and the fuel weight Wfuel. First, we must calculate the initial values for the thrust and the engine weight, as well as the thrust-to-fuel ratio. We assume that the aircraft is in equilibrium as it's flying at constant speed. Hence, the lift is equal to the weight and the thrust is equal to the drag. CD over CL was given and is 0.05. Hence, D over L is equal to T over W is equal to 0.05. This gives that the thrust is equal to 0.05 times the weight, which is 0.05 times 1 million Newton, which gives you 50,000 newtons. For the cruise thrust, you were given that the cruise thrust is equal to 0.2 times the maximum thrust. Hence, the maximum thrust is 5 times the cruise thrust, is 5 times 50,000, is 250,000 Newton. Next, we determine the engine weight. The engine weight was given as the maximum thrust divided by 2.083. Substitution of the numbers gives 250,000 over 2.083, which equals to 120,000 newtons. For the fuel weight, we assume that the thrust-to-fuel ratio is constant. The fuel weight was given as 400,000 Newton, and if we divide the fuel weight by the maximum thrust, this gives 400,000 Newton over 250,000 Newtons, which equals to 1.6. Hence, the weight of the fuel is 1.6 times the maximum thrust. To calculate the change in engine weight due to the initial weight savings, you take the difference between the starting value and the value you calculate next. The same applies to the savings in fuel weight. The total additional weight saving can now be found by adding both values together. Now let's do our first iteration. The weight is reduced by 2,000 kilograms or 20,000 newtons. Hence, our new total weight is 1 million minus 20,000 is 980,000 newtons. The thrust now becomes 0.05 times 980,000 is 49,000 newtons, and the maximum thrust at 5 times the thrust in cruise becomes 245,000 newtons. The new engine weight follows from dividing Tmax by 2.083333, which gives you 117,600 newtons, and the new fuel weight is 1.6 times the maximum thrust, equals 1.6 times 245,000, giving you 392,000 newtons. Now, all that's left to do is to calculate the additional weight reductions. The engine weight can be reduced by 2,400 Newton, which follows from deducting 117,600 Newton from 120,000 Newton. Similarly, the fuel weight can also be reduced by 400,000 minus 392,000, which equals 8,000 Newtons. The total additional weight loss, or snowball effect, is 2,400 plus 8,000, equaling 10,400 Newtons. If you now start your second iteration, you must first adjust the aircraft weight for this. Your second iteration starts with the weight of the first iteration minus the weight saving found in the first iteration, which gives 980,000 minus 10,400 newtons equals 969,000 newtons. And with that number, you start the next iteration until you have completed 5 of them. So this is what the first 2 iterations look like. And as you can see, the weight is slowly reducing. And after 7 iterations, we end up with a cumulative weight reduction of 41,444 newtons. In the previous question, you worked with a simplified version of the snowball effect, and several parameters were ignored. What other parameters could be used to further reduce weight? Describe at least 2 parameters. So let me discuss 4 possible parameters with you that you could have used. Reduction of wing area S, engine size, landing gear, and tail surfaces. A lighter aircraft requires less lift to stay airborne. Therefore, as weight decreases, the wing area S can also be reduced, and as a result, drag will also decrease. Lower fuel requirements means a smaller engine can be used, further reducing the weight of the structure. This also means that the systems and the structure supporting the engines and fuel transfer can be smaller. It is also possible that at some point 2 engines may be sufficient. If we look at landing gear, an airframe with a lower empty weight will be lighter upon landing. Therefore, the landing gear in the initial configuration may be over-designed for the optimized aircraft and could be made lighter. And finally, tail surfaces. A small wing area combined with lower aircraft weight mean that the horizontal and vertical tail surfaces do not have to be as large as they might be in the initial configuration. So hopefully you got most of the answers right. If not, please go back and check where you went wrong and work a bit more on the material. Do ask others for help. If you've only watched the answer video, then really, who are you kidding? There's no answer video with the exam. Because this may have worked in school, but here it is just asking to get yourself into trouble. You really must do your work. I realize it sounded like your mom, but hey, who else is going to kick your butt here? With that, you're all done for the structures and materials part of the course. For the exam, make sure you master all the material and use the homeworks, this assignment and old exam questions as practice materials. Don't learn them by heart, as the questions will always be new ones, otherwise I get bored. Good luck, and if you still have any questions, contact us using the discussion board.